My name is Yu Xie. I'm a professor of sociology, statistics, and public policy. I'm also a research professor at the Institute for Social Research, where I direct the Quantitative Methodology Program, QMP. Since year 2000, the QMP has been sponsoring an interdisciplinary seminar on causal inference in social science. As a tradition of the seminar, we host an interdisciplinary symposium on causal inference in social science at the end of the semester. So on behalf of QMP and the seminar, I would like to welcome all of you to today's symposium. I'm quite excited by today's symposium because we have two eminent scholars who have made tremendous contributions to causal inference literature with us today as our guest speakers, Dr. James Heckman and Dr. Judea Pearl from UCLA. The structure of the symposium is as follows. Between now and 3:30, we'll have lectures by the two distinguished guests. And then we will take a short break between 3:30 and 3:45, and we will resume the symposium with discussions from students and from the audience until 5:30. So let me now invite my colleagues to introduce today's speakers.
Hi, my name is Danny Almiral. I'm a faculty research fellow at the Survey Research Center at the ISR. I'm delighted today to present Judea Pearl. Judea Pearl is professor of computer science at the University of California, Los Angeles, where he has served since 1970. In the mid to late 80s, he and his colleagues began to make strong connections between his earlier work on Bayes networks. These enabled machines to represent probabilistic information parsimoniously and meaningfully, and connections between Bayes networks and causal reasoning. This is right around the time when the term causal Bayes networks were born. Since then, Dr. Pearl has been active in causal inference, unifying and making connections between the graphical approach to causality and the potential outcomes reasoning. Pearl has published over 400 manuscripts in 3 books, including his book, Causality, which is now in its 2nd edition. He's won numerous awards, and most recently, the Turing Award for contributions that transformed the field of artificial intelligence. Pearl used some of the proceeds from that award, this is interesting, to establish a new prize to encourage teaching of basic causal inference in introductory statistics courses. Please join me in welcoming Dr. Pearl.
Thank you for the introduction. I'm very glad to be here. I think I spoke here quite a few, maybe 3 times in my career, and every time is another thrill. I'm especially thrilled to speak to the seminar on causal reasoning. In my time, when I started this work, one wouldn't dream of having a seminar in such heretic title. So we made some progress. The title of my talk is a bit provocative on purpose. It's provocative in the sense that I'm going to talk about mathematics, so I excuse myself for not putting data or data on the screens. I'm not doing any data, and I'm excusing myself. I'm free to talk in the world of mathematics, and I know that you have a much harder life dealing with data. I talked with Professor Xie yesterday about the hard life of people who are dealing with real data. I'm free of that hardship. At the same time, the second provocative part of the title is use it or lose it, which means that if you want to brush it off and say, this is just abstract mathematics, I'm doing really substantive work, okay, you are going to lose something at your own peril. And that's my third provocative part. So I'm now to the outline. So I'm going to start with a causal revolution from Haavelmo to graphs and counterfactuals. And a brief summary of this period that took place, and I think it's about 50 years when Haavelmo first started. I'm going to focus on two fundamental laws of causal inference that if you have them, then you got it. And if you don't, then you are at the peril of not doing things right, or not doing the whole thing right, doing only partial things. And everything follows from these two basic laws. So it's a very condensed way of learning things. You got two laws, and you are on your own. It's like gravitational law, and what else is there in physics? Conservation of energy. Okay. And then, of course, application. I wouldn't deprive you of some of the victories. I call them victories in the sense that, for me, they were a surprise. So victory in my own perspective, things that I couldn't do 20 or 15 or 10 years ago, and I can do now. This is what victory is in my vocabulary. Please adapt to my vocabulary. Policy evaluation, misspecification test, mediation, generalizability from one study to another. Latent heterogeneity is just 2 weeks old, motivated by Dr. Xie. And then if we have time for frills, I'll be able to entertain you with song and dance. So let's start with Haavelmo. Haavelmo in 1943 published a nice paper, and that I think is a beginning, from my historical perspective, of the causal period in economics and in statistics in general. Of course, there were predecessors, such as Sewell Wright, geneticist in 1920s, and some of the works of early economists like Frisch. But I think at that point, the mathematics of causal reasoning got a boost, or it started. Haavelmo was looking at a simple two equations, supply and demand, two coupled equations with feedback, and notice that the term A, x, is not equal to the expected value of y given x, and raised the question, partly phrased in my language, when an economist put down an equation like that, what does he want A to represent? Okay. It's a psychological question. Notice. It's not, it doesn't have anything to do with economics. Okay. What information did the modeler intend A to carry in the first equation, and what information would A provide if we were that lucky as to estimate its value by some means? Okay. Since AX is not equal to the conditional expectation of Y, okay, as the normal naive answer would be, what did you mean by that? Well, you can say that perhaps A should represent some other property of the joint distribution, not necessarily the expected, the conditional expectation, but then perhaps A is some other functional of the joint distribution. I'm going to use capital P for probability, okay, for joint distribution, and use lowercase letter here for the values of the variables, okay? But the answer is no, it's impossible that A would represent. Number one, the equations may not be, may not be identifiable, in which case there isn't any G such that A would be a functional of the probability. And another reason is, even if A were some complex functional of the joint distribution, the economist is putting down this equation before he or she sees the entire set. Namely, the economy has a certain purpose for A to serve without seeing all the rest of the equations. right? It's incremental building of a model. So what does A represent? Well, his answer would be what later on I use the term do X, but he didn't use that, of course, but he meant that when he said, and here comes the next slide, that we are talking here about a new paradigm. A represents the effect of X on Y under a hypothetical experiment. So now we are moving to a total new paradigm. If until now statistics dealt with that kind of exercise, from joint distribution, which no one has, but theoretically it sits behind the data and spits out data, the duty or the job of the statistician is to infer some properties of the joint distribution on the basis of a partial data that this Santa Claus, I'll call it an oracle, spits out at his or her graciousness. This used to be a conception of statistical exercise. And the whole library and the shelves after shelves of statistical books deal with that exercise. Of course, Q can be very complex. Not necessarily the mean or the variance. You can have many variables and they interact very in a complex way. So Q of P can be a very elaborate kind of entity. But still, the paradigm is the same. You have data, and you are trying to infer the property of the joint distribution. If you have a joint distribution in a formula, you didn't have to go through that. And now we have a new paradigm. The effect of X on Y, which cannot be articulated in the language of joint distribution. There isn't such a functional, we said, we agreed, okay, so what is the exercise? Here is what Haavelmo envisioned. Someplace behind the scene, there is a data-generating model. We'll call it M. That data-generating model spits out a joint distribution or induces a joint distribution on the observable. That is behind the scene. That's the old oracle. Right? And we get some data from the joint distribution, and our purpose is to infer what? The effect of X and Y, which is not a property of a joint distribution. It's a property of a data-generating model. Okay? It's a whole new paradigm. There is something deeper than joint distribution. And that's what we need to infer, property of data. What does it mean? It's an invariant strategy or mechanism or recipe or law. Various philosophers and thinkers, including statisticians, gave different names to that entity. It's another oracle. What is it? It's a strategy by which nature assigns value to the variables in the analysis. For instance, nature looks at, before nature decides that the temperature of this bottle is going to be 37 degrees centigrade, nature consults other variables. The amount of radiation from this bulb, the amount of breathing that we have here, all other variables in the room, very complex, extremely complex, and go to some extremely complex computation and decide thou should have a temperature of 37 degrees centigrade, not more and not less. So that is a strategy which is invariant. It's laws of nature. That's all there is. Encoding of that invariant strategy of nature by which nature consults variables to decide the values, not the probability, the values of other variables. Because this bottle has a specific temperature, not a probability, a value. Good. Okay, now that we have a new paradigm, let's see how we react to that. First, it was a painful decrowning of a beloved oracle, because statisticians used to that as an oracle, a joint distribution. The accepted wisdom is that if you know the joint distribution, then you know everything. There isn't any higher wisdom than the joint distribution for all the variables which are observed. Right? And now we have to abandon this oracle. He or she was a beloved oracle. We knew how to do. We knew how to write textbooks in statistics. We knew how to teach and estimate. And now we have to abandon that and bow to a new oracle. And believe me, changing oracles is a most traumatic experience in one's lifetime. And it still hasn't been absorbed by most economists and statisticians. 52 years later, we hear from Holland. So in Holland, here we are in 95. I'm speaking, of course, about the equation here. What does it mean? Same equation that Haavelmo put down, okay, in 1943. What does it mean? And here's the answer. The only meaning I have ever determined for such an equation is that it is a shorthand way of describing the conditional distribution of y given x. Wrong. It has nothing to do with distributions. It has nothing to do with conditional distribution. Actually, it says nothing about the conditional distribution. It doesn't even constrain it. Okay. Next, a social scientist, highly respected, Richard Burke. Okay. Beneath all multiple equation models, there is only a set of conditional distributions. Again, you can't abandon your beloved oracle. Joint distribution. Next, you think that economists are free of that clinging to an old oracle? No. Here is we did a survey of 6 econometric textbooks, the most influential textbooks in the bookstore. And here's one of them, Stark and Watson. We actually took the 3rd edition, 2011. And here is a simple example. A state implements tough new penalties on drunk drivers. What is the effect? So look at that effect on highway fatalities. This effect is an unknown characteristic of the population joint distribution of X and Y. Wrong. It's not a characteristic of X, of the joint distribution of X and Y. It's a characteristic of the data generating mechanism that give rise to the joint distribution, that give rise to the data. That's what it is. Okay? And if you think it's idiosyncratic slip of a tongue, no, look at the Wikipedia, Econometric Models. No, Wikipedia is no, you can laugh at Wikipedia. No, I didn't. On the contrary, I tried to change it. I was tempted to change it and to correct it. But I said, no, I'm going to keep it as a witness to the current state of mind of ordinary economists. Okay? Those who bother to write the entries in the Wikipedia. So this is the state of mind. Structural equation is just a parsimonious way of encoding joint distribution functions. Okay. But Haavelmo had a different things in mind. He said to predict what the equation means, it provides policy advice. And he says it here very clearly, explicitly. Oh, I'm pressing on the wrong one. You'll have to give me a tape so I wouldn't press it. Oh, how do I go back? No. Oh. Too many temptations here. Yeah, oh, thank you. Thank you. Yeah. Oh, the next one. Good. The skeptic says, come on. How can anyone predict outcomes of experiments that were never performed before? Okay. You're going to predict outcomes of experiments from a bunch of equations. You, the analysts, never performed these experiments. How do you expect a policymaker to listen to you? Okay. Moreover, how can you encode them so parsimoniously? The policymaker may have a different policy to enact, to execute. And you with a bunch of 5 equations, you're going to advise the policymaker who is sophisticated professional. Haavelmo said that this is only natural because now the government, he's talking about the government control, is in fact performing experiment of the type we had in mind when constructing each of the 2 equations. Oh, so now you can come on. The economists who sit down and write the equations had in mind already all the policies that the government is about to perform or wish to perform or wish to evaluate. Out of your mind. The economists couldn't possibly have anticipated all possible queries that the government might want you to ask. How is it possible? Well, the answer is here. He says, here, look at the example. I'm going to give you an algorithm that will take the equation and give an answer to a typical question that the government might wish to ask. Suppose the government wants to impose a fixed income. So R is the income, and here it is. If government wants, right now R is a function of some other variables, U and V, and suppose the government wants to fix income, then the government will adjust the factors that currently influence income and adjust it by another fudge factor, GI, so that RI will remain constant to the level that the government wishes it to be. Okay? That was Haavelmo's surgery. I call it surgery because it modifies the equation. This is not what the economists wrote down. Right? And modified the equation, okay? And his 3 insights, I'm going to summarize it now verbally, what he did in his papers. 1, an economic model is a set of hypothetical experiments qualitatively encoded in a system of equations. Why qualitative? Because when you write down the equation, you don't give numbers to the coefficients. You let the data dictate the coefficients. So your input is qualitative. 2, an economic model is capable of answering policy intervention questions with no further assistance from the modeler. And 3, there is a formal way of taking an arbitrary model. The emphasis is on arbitrary model, not only the one that wrote, but a general algorithm. Give me your model, and I'll give you an answer to a policy question. Okay. Now I'll give you the evolution of causal calculus. From my perspective, Jim probably have different perspective. From my perspective, from Haavelmo until today. Okay. We saw what Haavelmo's surgery is, and it was replaced by Strotz and Wald by a real surgery. Wipe out the equation for Ri and replace it with a constant. Very simple, right? If your government wants to maintain a constant income, yeah? Previously R was affected by Ui and Vi, now it's going to be a constant. Just replace it with a new equation, and you have a new set of equations describing the world after the intervention of the government. Solve it, and that's the answer. Also 2 economists. Okay? That was before. Oh, I think I pressed on the wrong one now. Oh, no, it's here. That was before computer scientists got into the business. When they got into the business, they noticed that there is a very nice parallel between this wiping out of equation and operation on a graph. If R was previously a slave to U and V, now it's not going to be a slave, it's going to be a constant, which means the graph is going to change, which means that we now have to wipe out these 2 errors and make R a constant. So R is dangling on itself. And in terms of the distributions that we see, it has another operation, which is wiping out a factor. Here was the distribution before government enacted. Now the term probability of R giving UV is no longer effective. R becomes a constant. What do? Zoop! you cross out that factor from the decomposition, from the representation of the joint distribution function. Okay? And that was the manipulation theorem. When I got into that, and I noticed, and I, as a computer scientist, I said, wait a minute, wiping out an equation from a bunch of equations, I haven't learned that in high school. Used to solve equation back and forth, but never wipe out the equation and solve the rest. So, which means we have now a new algebra, a new operation, right? Wiping out and just solve. Okay, we in computer science are very sensitive to new operations. It has to be backed by semantics, by syntactics, by axiomatic characterization. It's not a simple matter to wipe out an equation. What happens when you do that? So I took it as a new operator, and I wrote it as do R. Okay? You do X, you do R, you make me laugh. You raise taxes. All these are do operators. Okay? And it has a new algebra behind it. And it's not equal to P of Y, given that I see R, which is the ordinary Bayes conditioning operator stands for. Obviously, not the same. Okay? If you observe the barometer down, you can predict rain tomorrow, but if you set the barometer down, it doesn't affect the rain. Okay? So two are different things. Okay, we all know that. I don't have to elaborate on that. I will only elaborate later about the algebra behind the do. Okay? And now comes the counterfactual. In 1995, we said, why only for the probability? How about the effect of X on Y on the individual? So let's talk about individual named U. Y sub R of U will be the value that Y would attend had R been small r. It's going to be the solution for Y in a R mutilated model. The model after you wipe out the equation for R. The equation that previously determined the value of R. Okay, that also calls for a new algebra, counterfactuals. So I'm going to go quickly now. I'm doing well on time, right? That was the first part. And it gave us the unification with the Neiman Rubin and with the philosophical work of Possible World by Lewis to put together all the work on counterfactual and causal reasoning. And now we don't have any questions left anymore in causal inference. Nothing. Which means everything is solved. I'm making it provocatively in such a way that you understand where I come from and you understand the limitation of mathematics. Of course, many things are unsolved. Okay? We don't know the effect of poverty, how to eradicate AIDS. We don't know that. But as far as the mathematics is concerned, we fully exhaust, we understand the limitation. And that's what I mean by solved. Okay? Because even if I tell you it's unsolvable with the data that you have, it's still a solution. If I tell you that you have 3 equations with 4 unknown, I saved you thousands and thousands of man-hours trying to solve it. It was a great invention. Like who was it that invented that? Kramer, I believe. Kramer Lou. That the number of, if the number of variables is greater than the number of equations, you can't solve it. Thousands of man-hours. So that is the limitation of mathematics. Okay? And we are at the stage where we can tell you, give me a problem in causal reasoning, and I'll tell you if it's solvable with the available mathematics and available, I shouldn't say available mathematics. The mathematics I'm going to present to you is the mathematics. There's not 2. Okay? It's only mathematics available. Yeah. So let's go and look at it carefully so I can expose myself with confidence to the critics that I see already on your faces. Only mathematics? Yes. Okay, let's go forward. Here is a causal model. Here is a description of nature. It isn't my invention. It's an invention of Newton and Galileo. Okay? Every variable is affected by other variables through a deterministic function. Oh yes, it doesn't obey the Heisenberg uncertainty principle. It's a Laplacian perception of nature, whereby the equations of nature are deterministic, and the only reason why we have probabilities is because of our ignorance of the boundary conditions. We do not know the uses, the probabilities on the exogenous variables. But we have here a bunch of equations. Here is a typical one, Bing. You're all familiar with that. Well, imagine that there are more complex equations, nonlinear, unknown. Okay? Everybody with feedback connected to anybody else. This is nature. But notice something, that if you assume that there is a unique solution, and there is a unique solution. Look, the temperature of this bottle has a unique value. Most values in nature have a unique value. If you assume unique value, no feedback and no outline, you have feedback in the equation, but you don't have runaway instabilities, okay, or multiple solutions. If this is the case, then the probability on the exogenous variables, P of u, and the bunch of equations that you have induce a distribution, P of v, and a graph over the observable variables. Okay? The graph is obvious. Every time you have a variable depending on a set of arguments, put arrows from the arguments into the variable. Easy. That doesn't take even a thought. But the fact that P of u induces a distribution on the observed variables, on the endogenous variables, this comes from the fact that you have a one-to-one, not many-to-one map. Okay? And that is nice because it also gives rise to some signatures of the structure that you can find in the observed distribution. I'll talk about it in a second. But now we have causal model and counterfactual. We can have every causal model like that is a generator of counterfactual with a very simple rule. Here's counterfactual. If I were a rich man, had I doubled the price, these are the way we talk to each other in ordinary language. It's also the basis of all scientific language. Had the mass been double what it is, had the gravitational constant been double what it is, I can predict how the moon orbit is going to be. Okay? Even though I have no experiment to conduct and change the gravitational constant. But we can do that. That is scientific language, counterfactual. And here is what the causal model says about the counterfactual. You want to have a meaning for that entities. Y would be small y. Had x been small x, I can tell you a way of computing it. And I can write it to you in 5 symbols. How to compute the counterfactual. Here, bear with me. Here it is. The counterfactual is a solution for y in a mutilated model, m sub x, where we replace the equation for x, the antecedent, with a constant. Okay? And we solve it. High school algebra. Solve it under the mutilated conditions, and you get yourself an answer to the what seems to be a hypothetical, metaphysical question, what the value of y would be had x been. Don't get excited. It's not metaphysical. It's simple high school algebra. Okay, here it is, the fundamental equation of counterfactual. Okay. Y can be computed by looking up the mutilated model, remove the equation for x, solve it. That is the answer to your hypothetical or counterfactual query. Solved. Next. I can do, once I have ability to define counterfactual in terms of computation on a model, wow, I'm almighty, almost. I can define joint distribution on counterfactual. It doesn't scare me. I just use the definition. You have 4 sets of variables, z, x, w, and y. Okay? Take any 2 combination of them, regardless of contradiction. Okay? Find the probability on that by simply summing up all the weights on the input that give rise to those 2 counterfactual occurring simultaneously. You want the effect of actions? It's a special case of counterfactual, where you have no conditioning. You simply said, I define do x to be the probability that y would attain the value small y had x been x. No conditioning. You want attribution. You want more sophisticated counterfactuals, like, for instance, what's the probability that Joe would have been alive had he not taken the drug, given that he is dead and he took the drug? Things like that. Complex, looks metaphysical, hypothetical, heretical. No, they have an answer. You give me a causal model, zoop, zoop, here is the answer. I can compute it. I can devise effective algorithm for computing it. Very simple algorithm, it turns out. Okay, now I'm on my way. Bing. With all the machinery of computer science and philosophy, we can now find the axioms to characterize the operation of mutilating a model. These are complete and sound set of axioms that governs the entity y had x been x. Okay? I don't ask you to look at it and evaluate each one. I just want to tell you that the famous one that you're using in the potential outcome, it looks like that. You see? You've seen this many times in many papers. Okay? This is just a special case of the composition. And there are four more. Most of them are technical. This is the working horse, consistency of composition. Okay? Now, why do we do the exercise of axiomatic characterization? Because if somebody comes tomorrow and says, I have a new definition of counterfactual. I don't want to mutilate things. I'm scared to mutilate models. Okay? I'll give you a new definition. And you want to see whether his definition is identical to yours. You just look at the axioms. If the axioms match, you know they are logically equivalent. For instance, in the potential outcome community, they have a new definition of, they don't have a definition, but they have something they call counterfactual, a potential outcome. And you look at what axioms they use, they just use these, nothing else, which means it's equivalent. I don't have to elaborate and to convince them it's equivalent. I just look at the axiom. So it's a signature of your semantics. Good. Now, Bing, the two fundamental laws of causal inference. I talked about one, we'll talk about the other. And then even if you chase me out here, for lack of time, I'll go back to Los Angeles fulfilled that I at least was able to convey to you the two fundamental laws with which you can derive everything I'm going to say, I meant to say, and everything that I will ever generate in my lifetime. Number one was the, here we are, was the law of counterfactual, how a causal model generates and evaluates all counterfactuals. What do I mean by all counterfactuals? Counterfactuals that are built from the variables that were in the model, that were under consideration by the model. It doesn't give you an answer to what Cinderella's hair color would have been had she been black. It doesn't answer that because Cinderella hair color is not part of the model. But it will answer all counterfactuals which are in the model. Everyone can be in the antecedent, and anyone can be in the outcome. Okay. Now, in addition to that law, we need one more, and I'm on my way back to Los Angeles. Here it is. The law of conditional independence, sometimes called deseparation. Okay. It goes like that. You have a causal model, and it has a certain connection there. Graphical separation in that model induces independence in the distribution. So this is how the world of causal relationship translates into something that we see. We see properties of the joint distributions of the V variable, the endogenous variable, the visible variable. So it tells you that no matter how complex those equations are in the F, And no matter how complex the distributions are on the U variables, okay, the structure of the causal model leaves a signature on something that we can see. So when we are lucky, we can reconstruct the structure there. And when we are lucky, we can test the structure. And that's the whole point of the deseparation business, okay? It's the window through which the causal model interfaces with the visible, what we can measure. What does it mean? It means that if you see separation between a set of variables x and y in the graph that you drew up from the causal model, it implies, logically implies, that you have conditional independence in the distribution that you observe. X will be independent on y given z. Okay? So some signature remains from the causal model, from the data generating model. It didn't completely get lost by the fact that we do not observe everything, or that we observe only, we don't observe the connection. All we observe is correlation, right? So here's the connection between causation and correlation. Something about causation is retained in the world of correlation. Not everything gets lost. And that is the second rule. You have these two rules, and I can take a flight to Los Angeles. Now I'm going to take the flight, I'm going to draw the implication with you. I don't want to leave you alone to do all this work, but these are enough, logically speaking. Okay? For instance, how do you read counterfactuals from an entity as innocent as structural equation model? Let's assume it is a linear structural equation, okay? Something that everybody is familiar with if you took Economic 101, Social Science 101. And you still teach from the book of Duncan? Yeah, you have that constantly. But nowhere in the book of Duncan I see counterfactual, right? This is an oracle for counterfactual. Not many people realize that. Well, let's go over it together. Together, here we are. What am I going to press now? This one. Yeah. Suppose it stands for treatment, some program, and Z is the amount of time students spend on homework, and here Y is the score in the exam, and this is some special training. Right? And the meaning of the graph is nothing else but these three equations. Okay, are you all with me? You want a question? Have a question? No. So let's move together. Zoop. Now comes the question. Ping. I submit it to data analysis, and I find that, well, I have screwed up symbols here, that alpha is equal to 0.7, beta is 0.5, and gamma is equal to 0.4. Okay? I put it down here. That is a normal exercise in structural equation model. Oh, 5 minutes. Good. I like it. I'll show you a revolt. It's all right. I'll be in time. Okay. Now comes the question. This is about the population. Right? Now I want a specific individual. I want Mr. Joe to come here on stage. Here he is. A student named Joe. He measured x equal to 0.5. He spent only 1 hour a week in homework, and his score on exam was 1.5. So I know something about x, y, z. And I'm going to ask a very penetrating question about Mr. Joe, not about the population, about Joe. What would Joe's score be had he doubled his study time? Study time is an endogenous variable. See? It's affected by the treatment, right here. Can we answer it? Yes. I gave you the first law of counterfactual. Mutilate the model, okay, and compute the counterfactual. Solve the equations of the mutilated model. Here it is. Zoop. You remove the equation for z. It used to be dependent on x. Now no longer. Now it's a constant too. Doubled the study time, right? Solve the new equation. Zoop, zoop, zoop. You get an answer. Zoop, zoop, zoop. Everything is zoopy because it's high school algebra. Once you get this, the structural equations are nothing more but oracle for counterfactual. They contain all the information to answer all the questions that you can hypothesize and pose with the variables available to you. Once you get this confidence, then counterfactual is no longer going to be scary. On the contrary, it's going to be your working horse. Now, I wouldn't talk much, because I don't have the time to talk about the confusion of the century. The confusion between regression equation and structural equation. The meaning of structural equation is that the B coefficient here in the structural equation is nothing else but the coefficient of x under the experiment. When you vary x, you control x, you look at the expected value of y, and it makes an empirical claim that you can test for. If you conduct this experiment, then you are guaranteed that the result of it is going to be independent on any z. Who is z? Z is some variables mentioned in the 27th equation, among the rest. You have a bunch of equations here. When you write down that, you mean that it's going to be independent. That's why I didn't put z in the arguments of y. Good, and we will go on and all the confusions of the world, and we are now in a new era. The era of causal analysis with common sense. This is what I mean by the 5 necessary steps for causal analysis. You can't miss any of them, and you have to address each one of them. First thing, which is the hardest one of all, define your research question. What is your query? And express your query. To be meaningful, it has to be computable from a causal model, for any arbitrary causal model. The color of Cinderella hair is not an admissible query because it's not in the model. The variables are not there. Okay. Here's an example of what you can put there, and I repeat if necessary if you have to modify the model, but here are some examples. Causal effect. I express it in a way that is computable for the model because I just told you how to compute counterfactual. Right? Mutilate, solve equation. So therefore, it's computable from any model, no matter how screwy. Here's an example. Average treatment effect, okay? Again, that's the do operator, computable. Here's another example. Dynamic policy analysis. You do something in response to some observation, some function of z where z is observable. Okay. Computable. Varying policy analysis. Many actions you take in sequence or simultaneously. Do x and do z and do w. No problem. I can mutilate 3 equations. Okay. Computable. Take effect of treatment on treated. Now I cannot use do anymore. It's counterfactual. So I write it in a counterfactual way. But am I scared? No. Counterfactual are as easy to solve, to compute, than anyone else, as do. Let's take, indirect effect. What the expected value of y is going to be if you fix x and you make z varies to the whatever value z would have gotten, okay, double counterfactual, nested counterfactual, if x were different. Not small x, but x prime. Am I scared of nested counterfactual? No, because it's just high school solution of equation. Good. So this is an example. Let's go from definition to assumptions. We have a golden rule of causal inference says you cannot have causal conclusions unless you have causal assumptions. And the causal assumptions are not verifiable by observational data. So you have to express the assumption in some form. I know of 2 forms which are very useful, structural and graphical form. Are there more? Yes, some people tell you they can do it in potential outcome language. Okay, so let's go together to the world of potential outcome and express, take a simple example, and express the assumptions in two ways. One, we'll express it in a structural form, and the other one in a potential outcome, in case some of you are sold on potential outcome. Okay? Here we are. 3 languages, same example. First will come English. English is a good word we can express assumptions. I assume that the effect of smoking, X is smoking, Y is cancer. The effect of smoking on cancer goes through a tar accumulation in the lungs. And we also have a confounder, a genotype U, that simultaneously make people crave for nicotine and put them in a high cancer risk. Okay? So we have a confounder. I explained to you in English. Okay? We are all together. This is just a mnemonic in terms of graph. Dismiss it. But English is one language to express assumption. Now I go to the potential outcome and express everything I said in English in a potential outcome language. Okay? You have only one symbol, and this is a variable subscript another variable. That's a head. Potential outcome means the value of the outcome had the input or the treatment being whatever you find in the antecedent, in the subscript. Zoop! This is how it looks. Don't test me here because I tested it about 12 times. And I defended this to be equivalent to the English description, okay, in front of the disciples of Dan Rubin. So they tested every symbol here. This is what it is, what this conveys. Here you have exclusion relationship, and you have conditional independencies among counterfactuals. This is the way to express it in a potential outcome. Okay? And I'm asking you a simple question. Is it friendly? I'm asking you, is it consistent? If you look at this, can you tell if there's no contradiction among them? If you look at them, can you tell whether they are complete? If all the assumptions are included there, you haven't forgotten one? Can you tell me if they are redundant? Perhaps one of them follows from the other. And can you tell me if they are plausible? Now notice the strange things. I eliminated the graph, okay, for purpose to walk together through the dark world of Dan Rubin and Imbens and others that are working in that darkness. This is how they think about the world. It's a black box, and you are allowed to make assumptions, but in this language. 1 minute, good. Okay. Can you tell me if these assumptions are plausible when you think about cancer, tar accumulation, and smoking? Okay. This is a dark world. Okay. And the last question is it testable? Now, this is now a mathematical question. Forget about darkness. Can you test if this have any testable implication? Okay. This is your alternative now. You want to use structural equations, or you want to use potential outcome. And now a third language, Zoop, structural. You don't like graphs? Fine. Use a structural equation. These are non-parametric. You don't know the functions. It can be arbitrary. You know only that the disturbances are independent. This is equivalent, mathematically equivalent to this. I can guarantee it to you. And I can walk together with you and solve the causal effect of smoking on cancer using that language and using that language. Each one its own calculus, okay, has its own calculus. And in my book, actually, I solve them in 2 different ways. One in the calculus of potential outcome with its axioms, and the other one is with the calculus of structure, which is a graphical calculus. You give me today any graph, which means any set of non-parametric structural equation, and I can glance at it and tell you yes or no, which means give me any 2 variables, x and y, and I can tell you if the effect of x and y is identifiable or not. And any one of my students can do that. All it takes is 4.5 minutes. 4.5 minutes to master the diseparation. But this is an investment that I cannot get people to invest. So here you have the whole generation of economists writing textbooks after textbooks, talking about identification with IVs and without IVs and with the moment and all this, and they don't know that the entire subfield of non-parametric structural equation is solved, absolutely solved. Let's go to identification. Oh, here's identification. One more thing. Yeah, solved. That's what I was aiming at. Now I can leave. Here's an example. I'm going. Oh, okay. That is my luck. Please ask me to continue when you're in the question-answer period. No, actually, I tell you, I'll go very quickly on them, just to tell you what you're missing, to give you the flavor of what you're missing. It's going to be very fast. It wouldn't take much time from Jim here. So you're giving a structural equation, a set of structural equations. The functions are unknown, and you're asking a simple question. Because they are unknown, the same information that you have in them, you have in a graph. We haven't lost any information. Zoop. And I ask a question, for instance, what are the testable implications of the model? Okay? Look at it here. A typical example from textbook for Economics 101. Can you tell if they have a testable implication? And the answer is yes, second law of thermodynamics, right? It's right here. Yes, look at the graph and look at all the missing links. Because whenever you have a link missing, you have a separator that separates them apart. Okay? Here are the missing links. Z1 and Z2 are separated. Don't look at the collider because that doesn't constitute a link. Z1 is separated from Z2. Z1 is non-adjacent to Y. See, non-adjacent. And so on. List all the separator. Okay? And then you have implication, which means in the observed distribution, you are guaranteed to have Z1 independent on Z2, Z1 independent on Y given these three variables. And if you do regression analysis, then you have the partial correlation being equal to 0. That's what the model dictates. You go and test it. Next. Some people test robustness using all kinds of gimmicks, adding and deleting regression or variables in the regression. They're all implied by the graph. I wouldn't even talk about it. Next question. Intervention. Can you compute the effect of X and Y? Answer is yes. Could you give me a set of variables that if you were able to measure them, you can adjust for them and get the correct, unbiased estimate of the cause effect of X and Y? The answer is yes. And this is one of the victory. Okay? You give me a set of variables and tell you which one you must measure. And for instance, suppose you cannot measure any of the top ones. Is there a single variable if you measure, you can get an unbiased estimate of X and Y? The answer is yes, W3. It's called an intermediate instrumental variable. And all these gimmicks, here's examples taken from sports medicine. Some people cannot read graph if you have symbols on the graph. They need to have anchor to specific application. So here you have an application that's warm up, increase injuries, or reduce injuries. Bunch of variables you can measure. It turns out if you measure this, all these sets, all that set, you're okay. Otherwise, you're not okay. Bing, it all follows from the one simple laws of thermodynamics. Here's how the calculus works. A bunch of rules you can apply. Here's how I solve the cancer smoking business with the calculus of do. Just a flavor. I don't expect you to follow that. Rule after rule until you remove all the do operator, you end up with something which is measurable. Bing. What else calculate. You can find instrumental variables, for instance. You can make a variable which is not instrument into an instrument by condition on other variables. All kind of beautiful things that I'm sure that everybody from the potential outcome community will rejoice just knowing it can be done with 4.5 minutes of investment in the second law of thermodynamics. Okay, what else? Equivalent models, identify counterfactual like ETT, find the causes of effect, mediation, which is the second victory, external validity, which I wouldn't have time to talk about, okay, victory 2 and victory 3. And so what am I advocating? A symbiosis between structural equations and potential outcome. You articulate your assumptions in the language of structural equation or graph, which is part of structural equation, and then you go to, if you really want to, you go to the algebra of potential outcome and derive answers to your query, or you stick with a graph, because everything can be done in the graph because of the logical equivalence between these two languages. I'm sorry that I wouldn't be able to entertain you with the transportability and external validity solution that we have, but please ask me about that in the question-answer period. Thank you.
Most of you know who I am. I'm Jeff Smith. I'm a professor in the economics department and also have appointments in the Ford School and Institute for Social Research. I am honored and delighted today to introduce Professor James Heckman. Jim is the Henry Schultz Distinguished Service Professor of Economics at the University of Chicago. He's the author of more than 250 articles and has more than 85,000 Google citations. That total includes one individual paper with more Google citations than all of my papers put together. Probably you can guess which paper that is. Jim won the John Bates Clark Medal in 1983, and I had the good fortune, along with Petra Todd, to be at a conference in Rio with Jim the day he learned in 2000 that he had won the Nobel Prize in economic science. Most of you know that Jim was my dissertation advisor at Chicago. I like to describe my experience of interacting with Jim as doing intellectual crack. The high is amazing. It is very addictive, I can assure you. Even in the Nobel-rich environment at Chicago, Jim stood out for the breadth of his knowledge. I can remember discussions of burial mounds in Sweden, of Mayan ruins. That was in a hotel late at night in Haavelmo. World War II German generals. The history of IQ testing in the U.S. Jim stood out for seeing connections that others could not. And Jim stood out, finally, for his way of integrating the economics with the econometrics in his research. That's the thing, the primary thing that drew me to work with him as an advisor. And it's something that we're going to hear more about right now. Join me in welcoming Jim Heckman.
That's the reversal. Okay, is there? I need some water. Yeah, that's good. Thank you. Okay. Okay, well, thank you very much for that introduction. I appreciate it. I'm also appreciated very much Judea's lecture. I've known Judea, I don't know, at least for 15, 17 years. I don't know when the first time is you came through the University of Chicago, but we've been talking off and on at least for 15 years, and I think it actually was a little bit longer. And actually, as you will see, there's an amazing amount of agreement here, and maybe more than you want for a debate. You probably want hostilities and saying this guy's an idiot. He's not. But I would say the following about what he said, and there's a lot to agree with, but I think looking at this, and maybe it's just a phenomenon of getting old, I had a sense of sorrow in the sense that Judea has written, and I think correctly, that a lot of econometrics textbooks these days don't really contain very much of the causal calculus. But I think if you go back in the history of economic thought, there was a famous book written by Mary Morgan called The History of Econometric Methods, some 22 years ago published, I think. And she reviews this exactly the Frisch, Haavelmo, Coles Commission logic. And I would just remind people, if you go back, in fact, there's some wonderful essays that have been recently collected by Olav Bjerkholt, whom you know quite well, at Oslo, who actually puts together some of Frisch's early lectures, actually lectures at Yale in 1930, where he is addressing the kind of question, exactly the kind of question that we just heard about in the previous lecture. Namely, what those guys were concerned with, and I think it's important to keep in mind that this was exactly the goal, and it was, and this was something that was a burning question. Starting in the late 20s and early 30s, Frisch, and I think it was really Frisch in Oslo, had this deep passion for trying to understand economic policy. And I think that's been the main goal of a lot of research in econometrics. And it crystallized in the work of Haavelmo and the work of Frisch, and then all the later work of the Coles Foundation Econometrics, or Coles Commission Econometrics. But what were they concerned about? They were concerned exactly about this range of questions. They wanted to know what would happen if I changed certain policies. How would I affect the world? So if you read those early essays, what you're going to find is an amazing amount of insight and concern about issues about structural invariance, which I'll come to in a minute, but really trying to understand how they could take policies that have been implemented today, data that they implemented with current data, and make out-of-sample forecasts. Not only the question of so-called external validity, but considering what the effects would be of new policies. And so in the course of doing that, they created what I call the structural model, what they call the structural model. In fact, the classic of all this, the culmination of this line of work, was not Haavelmo. That was really an initiator, an important initiator, but I think the most important persons were those who worked in this monograph 10 of the Coles Foundation, Coles Commission in 1950, where they put together the theory of identification, structural estimation, and they were concerned exactly about whether or not we could forecast policies out of sample. And so they were really dealing with what I think you would call structural analysis or causal analysis. And I think, to be perfectly fair to them, I think that they really did pioneer a lot of the work. Now, that's not to say that that work has been fully appreciated even among current economists. But I could certainly tell you some people in this room, I see Jeremy Fox sitting there, would be an advocate, would be certainly an example. There are many others as well. Bob Willis and his paper with Sherwin Rosen and so forth. So let me just say that I think there really is a full appreciation for what you're saying, Judea. I think it's interesting to put these languages together, and we're on exactly the same page that the counterfactual analysis and the structural analysis really are alternative ways of reaching hopefully the same kind of conclusions. Only I think that the econometric approach that was pioneered by the Coles group really tried to go even further than you're going today. So let me just try to go through this talk. I'm going to run out of time like he is, although I'm going to take all the time he took. So I was carefully timing it. So the original topic, the original paper was this Haavelmo paper in 1943. I want to talk about it briefly, just because it really, to my knowledge, was the first paper that formalized this old idea that I think, at least Steve Stigler says it goes back to Ewell, correlation is not causation. You hear that every day. Everybody says it. They go ahead and make causal statements after doing the correlation. But that's another story. Secondly, I want to talk about the DAG approach. And so in some sense, this is kind of an interesting role reversal. I'm going to be talking about DAGs from the structural equation approach. Then I want to talk briefly about simultaneous causality and mediation analysis. I also want to talk about a framework for unifying alternative causal estimators. And I probably won't be able to cover it in great detail, but I will link it back to Haavelmo and simply say, sitting there are latent variables, and I think you have the same notion. There's latent variables that were in his talk. And I want to try to unify the different methods as different ways of approximating this latent variable that gives rise to causal inference questions. Then I want to just lay out a very simple identification framework, and if time permits, talk a little bit more about mediation, but I probably won't have much time. So what is the goal of the econometric approach? And I'm more than happy to be interrupted. I have plenty of good economists in the room, and they can tell me, keep me on my toes. So what's the econometric approach? And it's exactly, the econometric approach to causality is developing explicit models of outcomes. Those are the structural equations we just saw. It also, and I think this is a really important feature of the model, understands the relationship between treatment outcomes and the treatment choice mechanism. And a careful accounting of the unobservables in these equations, in these structural equations, I think facilitates the design and interpretation of estimators. Now, what does the econometric approach do? It really is considering a range of questions. Just like the early pioneers, the Coles Commission group and Frisch before them, we're considering trying to evaluate different aspects of policy. Now, there isn't a single outcome of a policy. I can give you chemotherapy, and that can actually cure your cancer. It can also cause you an enormous amount of pain. It can cause your relatives a lot of pain. There are many treatment effects, some subjective, some objective. And it really does, the framework that I'm going to talk about really does essentially allow us to incorporate both of these. It's a model that also allows for simultaneity, which we know is important in terms of pure effect interactions, and we know it's important in terms of a lot of social interaction models. And I think we really have to make a distinction between these models and the methods of identification. And so the structural approach is really going to do this. But let me just lay out 3 questions which I think should be carefully distinguished in any kind of analysis. See, I was telling Jeff before that when I get into seminars on causality, I have a feeling like a recovering alcoholic, getting near a bottle of vodka or something, and my hands quivering, because I have a bad feeling every time I get into the causality literature, because I'm really not interested in causality per se. I'm interested in these kinds of questions. I think, and that's what the Coles people were interested in. Namely, these 3 kinds of distinct questions. The first question, I would argue, receives the most amount of attention in the potential outcomes literature. It's basically evaluating the impact of interventions on a particular outcome, whether it's a subjective outcome or an objective outcome. And we could have a lot of different parameters that we might want to think about. So that's a question which is saying, does the aspirin work? But then our population for evaluating the aspirin, say, would be New Guinea natives near the equator. And we might like to ask, does the aspirin work somewhere else, say in northern Siberia, or maybe in central South America, or something of the sort? And that's exactly the question of going out and extrapolating. And again, this question of external validity. Do the structural equation parameters transport? Again, a theme of Coles Commission econometrics that was developed, and I'm glad that Judea is on board on this. I would say that the train was pulling out of the station maybe 60 or 70 years ago, but I'm glad you're on it. I'm happy to have your membership. But the third question is the one that many people have talked about, and is really the one that was probably the one most paramount in the minds of the Coles group. And that was forecasting the impacts of interventions never previously experienced. One of the primary examples, we have a new tax policy, fundamentally different tax. Like the U.S. proposes a new income tax in 1913. It puts an income tax into place. What is the effect of this? Or in McFadden's work on transportation, what happens when we build the Bay Area rapid transit system in San Francisco? And that's exactly the challenging question. And the structural parameters that were brought in there were designed to address those questions. And so I think we really need to think about, when we look about causal inference questions, to think about what policy question we're looking at. Because as we go down this list, we get to a harder and harder set of requirements. Many people say this is basically impossible. And you might not believe all the ingredients required. You could make your assumptions explicit, but if my assumptions included things like, well, the Martians are going to land right in the middle of my dam site, and that's going to give me some some leverage and allow me to do. I mean, if I start making those kinds of things, I could have a structural equation that describes it, but very few people would believe it. But that you could still have an algorithm for saying when you would do it. So I think we want to keep these intact. Most people feel very happy to answer a question like P1. Does the program work? Doing P2 is tough, but it's interesting and it's highly relevant when we look at policies, and frequently isn't that often considered, but it is considered in certain literatures. 3 many people are just frightened of. Okay, so what are the 3 distinct tasks in causal analysis? And here I want to separate out 3 different problems, which I think is really important. And I think Judea and I are in complete agreement on this kind of separation. First of all, it's the question of where does the causal model come from? And completely, I don't know if it's Galileo, but we have conceptual frameworks. In economics, we have certain kinds of economic theories. They may not be agreed on by everybody, but we have a class of hypothetical models. And these models essentially consist, if you want to think of it, as experiments, mental experiments, or experiments where we just imagine if this, then that. So that's kind of one important task in causal analysis. And that's something that we can't really describe in an algorithmic way. I mean, there's a whole books are written about the logic of scientific discovery, how we can actually create ideas. And this is something where there's an infinite class of these models. And we can always come up, the most clever minds can think of many, many different explanations and many different models. And winnowing these down is important. But we have rules. And I don't want to get into the philosophy of science, but we know that that's a task 1. It's very different from task 2, which is saying, given a set of models, can I identify them from the data, or can I winnow them out? And that's a very different kind of activity. That's going from the data to actually trying to see whether or not the model is consistent with the data, or we have a bunch of models consistent with the data. That's a key question. And then there's a third task, which is frequently confused with the second, but it's really separate, and that's just estimation issues. How well can we precisely define? So let me lay out what I think is a prototypical model here, which many of you have seen, and I think you could think of it. I think this is a prototypical model of policy evaluation where we have 2 outcomes. And I would say, I don't know if you'd call this a potential outcomes model. I would say it's also a structural model. And let me give you, for people familiar with Bob Willis's paper with Sherwin Rosen, you'll recognize the ingredients, or at least some of the ingredients. Namely, you have these 2 outcomes. Say you're educated, your earnings, present value of earnings if you're educated, Y1, the present value of earnings if you're not educated. There's a certain direct cost, say tuition costs. And then in addition, there's information. So agents may know more or less about expectations, what they're going to get a lot. There may be some uncertainty. And so agents, there are decision rules in which agents make decisions based on these ingredients. So that's kind of a key aspect. And so one rule, not the only rule, and many different rules have been put forward in the literature, is saying, well, agents with a certain information that they have will decide to go on the basis of expected gains from this activity. And so this is like a basic prototype, the so-called Generalized Roy Model. And this model, I think, is extremely important. And it's also a challenge, by the way. It's a challenge for even some of the methods that Judea was talking about. But the Generalized Roy Model, where we have heterogeneity, partial information on the part of agents about when they make their choices, different information after they realize their choices, at least on the choice they executed. So we have a bunch of treatment effects here. So this is the standard treatment effect, but we also have ex-ante treatment effects, what people expect to get, and gross gains. You could have an expected net gain and so forth. And the statistical approach, in some sense, not really a model, and I would put this as somewhat different, I think, in terms of the causal inference literature, that I think that one of the main contributions of the structural approach, or the econometric approach, is exactly modeling the relationship between the outcomes, the potential outcomes, and the choice equations. And then also recognizing there are a bunch of different policy questions you could ask. One policy question is this 8 question. What's the effect of putting somebody, on average, putting, say, everybody into the college sector or everybody into the high school sector, and then comparing the 2 outcomes. That's not a very interesting question in that particular issue. But more interesting would be questions like, what would be the gain? What would be the expected gain? Or what would be the gain to people who are just indifferent between going to school and not? What's the marginal gain? Each of these is a different policy question. And we can also talk, to advertise some of our former papers, distributional treatment effects. So there are a range of treatment effects, and I can't tell you there's a paramount treatment effect. I can only tell you that there is essentially a set of policy questions. And I think this is a very important difference between the approach that many people in causal inference take and people in econometrics take. And that is, the question drives the choice of method. I want to know something about this question. There are different rules, different ways to achieve it. And the more ways we have, the better off we are. But there's not a universal algorithm, and there isn't a kind of a universal causal question. So it can well be that some people are interested in one aspect of a problem, they're interested in others are interested in another aspect. Okay, so enough philosophy. Let me just lay out, we've already seen an example, so I'm not going to go through it. This is an example of a structural equation, y, equation 2, where basically we imagine, and this, I literally use the word imagine, as did Frisch, as did Haavelmo, as did Koopmans, and there's a whole group, that we write down an equation. It's a structural equation, and it's a thought experiment. It's a mental exercise where we say, I have x and I have u, and I have a functional relationship picking x and u, determining y. And this, I think, is standard. In the more recent work in econometrics, we allow there to be some uncertainty. So we can get to Heisenberg. We can say, this would be stated in terms of ex ante expectations, and then we might get shocks that are realized. All the work in Euler equation estimation, all of that work essentially. So what's the key feature in this model? And this is something that I would say is really important. And it keeps being rediscovered. And the fact that it's rediscovered is not a bad thing. I'm really not trying to take credit away from anybody. I think it means these ideas have a recurrent, enduring quality. But so this is just formalism, saying it's a function, it maps. But I would simply say what we have as a property of this function is invariance. What we want to be able to say, and this was carefully formalized in the Coles Commission notion, that when I change x and u, I don't change the function g. That's your surgery. It could be that I do change that. In fact, there's a whole literature, the so-called Lucas critique. Marshak anticipated that before him, where if I change certain arguments, I will change the structure in the system, and I need a deeper structure. So this was the issue. So Frisch has this paper in 1938 writing about exactly this question. So the stability of the system. So surgery, as many economists have pointed out, is not a costless thing. If I shut down an equation, I could change the whole behavioral nature of the system and worry about that. So that was an issue, and it's a non-trivial issue. I mean, it's true, by the way, if many of you looked at some of David Hendry's papers, he was never able to really find that policy changes were changing structural equations, even though it was feared that was a problem. But nonetheless, it was a deep fear to try to get stability and structure. So this equation is sometimes called the Marshallian causal equation, equation 2. Why? Because it's telling you when I change x, I hold u fixed, I hold u constant, that this is a so-called ceteris paribus effect. So that's what Marshall was writing about, and whole textbooks are written exactly on that subject, and we can put in uncertainty. So let me go to Haavelmo, just very briefly, because you've heard about him, and I think he's it's a touchstone. Because even though Frisch had all these ideas, Frisch was sitting isolated in Oslo, and Frisch exported all of his students around the world. And Haavelmo had the delightful experience of being in the United States just at the time that the Nazis invaded Oslo, or invaded Norway, and he hooked up with a bunch of leading statisticians like Abraham Wald and the Coles Foundation group, and they nurtured him. But here's the equation. This is not going to shock anybody, I hope. This is the same regression equation that Judea was putting on. And what the Coles group, in particular Haavelmo, was saying is the following. We have an outcome, we have x, and so literally it was an experiment. It was a thought experiment that wrote that equation 4 embodied. I think Haavelmo was extremely explicit about this. The distinguishing feature was essentially modeling not only that there was an x-y relationship, but thinking there could be some other cause. In the literature, this is called an all-causes model. You know, I can put uncertainty on this as well, saying x pose shocks. But I have an x and I have a u, and the problem is if I just run a regression of y on x, we've known, and I really honestly believe we've known this since Haavelmo's paper, that in general we don't recover beta, which is the policy parameter that comes from manipulating x. And I think Haavelmo is quite explicit. Haavelmo states it slightly differently, and I would just give you his formalization. I'm having trouble here. Yes. This is Haavelmo. So the distinction that he makes is the following. He wants to distinguish between fixing and conditioning. So I think it's very similar to this do apparatus. Not identical, but similar. So in terms of the literature, basically he's saying, okay, E of y given x, we see immediately this problem, which is in the third bullet, which is we pick up the correlation between u and x. And so we know that changing x, we're getting an average relationship. Haavelmo discusses it. And fixing x is a totally different activity. And Haavelmo makes this point explicitly. So that's a hypothetical manipulation. Equation 4 is a theoretical construct. Okay. And that's exactly the Marshallian clause. One addition to the literature that I want to talk about, and it's an important addition that drove a lot of the research, is a paper by Marshak and Andrews that came 1 year after Haavelmo, published in Econometric. Many people claim the Marshak and Andrews paper is the first structural paper in economics. I think it's true. It also has a lot of discussion of partial identification, but that's another story. What we look at here is the u, again, the u in the equation, depends on two sources, v and epsilon. And so he thought, okay, there's some random variable out here, and the random variable is going to be v, driving u, and there's also some other source. And so when we compute the expectation, the problem isn't just u, it's the component of u that's attributable to v. And so this shows up. This v is going to show up in just about everything else I do, assuming I have any time to do it. So let me now play an interesting game. I'll be curious what you say about this. So I'm going to enter the world of DAGs. So here I am, daring my debating partner or whatever. But I want to simply go back to a formalization within the Haavelmo and I would say the Pearl frameworks and make this distinction and see whether or not it passes your test. You may say I fail. That's okay. I will disagree, but nonetheless, we'll. But we make the distinction between the hypothetical model and the empirical model. So the empirical model is exactly the data generating process. And I couldn't agree more, though. It's a whole cluster of people saying, whatever it is, we just run an empirical relationship. That's going to be the basis of policy. But I see a lot of very informed minds in this room. And I don't think a lot of them are saying that personally, but that's another story. The distinction between the two, they have the same domain. And here we get to the fresh notion of autonomy, that the domain of definition of the structural model. So y depends on x and u, and x depends on v and omega. That for both the empirical model and the hypothetical model, we have the same set of generating equations. Okay? That doesn't mean that x and u are correlated. This is just basically saying for the same values of x and the same values of u, I'm going to get a y, I'm going to get the same values of x for a v and an omega. Okay, and a particular example is the Haavelmo paper. So I think I should skip some of this stuff now, because everybody knows this. You've been reading Judea's papers. You know all about descendants, parents, or you do or not. But basically, just to map it in, for those of you, just for the fun of it, we have basically the parents of y. Remember, that's our outcome equation. They are the ones that directly cause y. And I'm not saying I have an algorithm for determining causality. I'm simply saying I have already announced it, and I'm going to use this notation to describe it. So these variables cause y, and basically we have a distinction between what are called external variables and internal variables. Variables that are determined within the model and variables that are determined outside the model. And that's a useful notation. And so again, the same idea that hypothetical random variable, that these are constructs. So here, let me just lay out. This may be more notation than you want. It's certainly more notation than you put up, so I should worry, but here I am going to do it anyway. So we have a hypothetical model, and there's only one new idea here. And so it's not so deep, but it's useful, and I would be curious. I couldn't resist this temptation, so we're going to do it. So we have a bunch of unobservable, a bunch of variables, x, u, and then we introduce a variable called x tilde. That's the hypothetical variable. That's going to be a random variable. So one of the biggest issues, it seems, and I think Judea is absolutely right, that if you go to the statistics community, the difference between conditioning and fixing is not very well understood. I thought I understood it, and I think I did from reading this early work of the Coles group. But I remember giving a seminar in the statistics department at Chicago some almost 30 years ago, and Billingsley was there, Bahadur, many very good people, Paul Meyer and so forth. I was writing down what was a simple structural model, and I was actually making this distinction. And I spent the whole seminar making the distinction between a conditional expectation and the structural model. So I completely agree with him, and to the extent that he's educated the larger human race in these ideas, it's a good idea. It's a wonderful contribution. Let me just do this graphically, because I'm not going to have time to cover all these equations. So if you look at this graphically, basically this is the idea. That we have a model out there. This is the hypothetical model of Haavelmo. And so x tilde is causing y. That's our pure thought experiment, right? And this is basically saying, okay, v, this is this transmission variable of the Haavelmo. V is causing x. We have some omega also causing x. Then we have some epsilon and u feeding together causing y. The thought experiment is this thing here, a manipulation. That's fixing. Ah, you're shaking your head. You're good. I like that. So, but now, here's the opposite. So instead of going through all the equations, I'll just go through the graphs, because I have no time for all the equations. This is the data generating process. And so we just compare these two. This is the thought experiment. And now within this model, it becomes trivial, I think. And I think this is a contribution to literally say, okay, now I can think about conditioning on x tilde. That's a properly defined random variable, and that's your do operator. That's essentially fixing the x. And I think it's important to clarify that, and I see that as an important contribution. Well, okay, I'm going to skip. So we've already heard about fixing, conditioning. I'm going to skip through a lot of this because I have no time. Let me just talk, just to say that there is a literature. Let me just talk very briefly here. Oh boy, I'm starting and I'm running out of time. This is a bad issue. So let me just sketch a few ideas. And I'm going to take people here at Michigan back to something developed here at Michigan, Klein and Goldberger, the dynamic fiscal impact multipliers back in 1955. And so if we go back just to the issue of defining causality and so forth, this system of simultaneous equations, which we saw an example of in Judea's last slides, is essentially a framework which allows us to do mediation analysis and allows us to address some of these questions of causality and identifiability. So I put it up because it's so familiar. So this is a linear simultaneous equation system. Y is a vector. X is a matrix of variables. B, this is a standard simultaneous equation system. And I'm going to say that X is external. It has no parents. It doesn't have to be the same as exogenous. So X could be, but let's put that to the side. So, and then gamma is full rank. Let's just go through that. This is a linear parameter all causes model. This goes back surely to the 1944 paper of Haavelmo. And the notion of Frisch and the notion of Haavelmo was basically that we could look at a class of interventions that were invariant to different manipulations. In fact, in the end, the final statement on this is a paper by Hurwicz, published about 50 years ago now, where he defined structural to mean parameters that were invariant to certain classes of interventions. So they could be completely non-invariant to some interventions, but invariant to others. Okay, so this is the standard model. And nonlinear systems can be postulated. Your colleague Rosa Motzkin has done a great deal of work on this. And so we can essentially generalize virtually all this idea. So I raised the following questions. Can we think about ceteris paribus manipulations within this model? Or do we have to do surgery, as you were describing? How can we think about causality? This is highly relevant. This is a model of social interactions I'm about to give you. In fact, almost all the work on linear social interactions models are basically applications of simultaneous equations models, and all the non-identification problems come from special cases of simultaneous equations models. So that's just a side issue. So it's relevant even to work today. So the question is, are the ceteris paribus manipulations associated with the effect of varying one component of y? Remember, that's an internal variable. Can you come up with a causal explanation? How can you do this? So let me just give you a very simple example. Two equation, two agent model. So basically, y1 is the outcome of agent 1, y2 is the outcome of agent 2, and we write down an equation where we my smoking affects your smoking affects my smoking. That's a relationship, okay? So again, I don't want to insult everybody's intelligence here. This is a standard model. What I've come to learn, though, when teaching this, is that each year when I put this up, fewer and fewer students in economics know this model, which is kind of sad, too. They're rediscovering under different names. That's fine. But let me just go through. So this model really does capture the idea that y2 could cause y1 and y1 could cause y2. So the question is, can we define structural? How would we come up with a notion of structural parameters within this model? So let me just give myself the simplest framework. The U's are going to be, the X's are going to be truly exogenous. They're external. They're unrelated to the U's. I'm going to have completeness, so I have full reduced forms, well-defined. And I'm going to try to look at Haavelmo's definition. So if I go back to the equation, I'm claiming that I can talk about gamma 1, 2 as the causal effect of y2 on y1. I think that's a legitimate interpretation. But how do we actually obtain this? And here I'll just share with you some dialogues I've had over the last 15 years with various people about this system. So what do we know about this system? So under completeness, we can solve out for what's called the reduced forms. And the reduced forms embody all this information you were talking about. So we put restrictions on the pi matrix that come from restrictions. In fact, that was the whole calculus that the Coles Foundation group did, going from the reduced form and asking, what can we infer back about the structure? So without, this is just what that happens to be. I'm not going to go through that. Now, the question is, without any further information on various parameters, you can't isolate the causal effects from the reduced form. That was the main point. The model's not identified. That's a standard identification problem. And the reason is because if I go back up here to this equation here, and I say I want to look at the effect of changing y2, holding x1, x2, u1, and u2 fixed, there's no variation. The model is fully determinate by those. So there is no variation. So you'll say, oh, something has to give. Okay. So there's an exact dependence. And that, by the way, that's true even if I get rid of the u's. There's no need. I can have, this is a question, again, of linear algebra. So then the question becomes, can you even define causality? And I'm telling you, many people have taken both sides on this argument, say I can or cannot define causality within this model. But there's no mechanism that's been yet stated to vary these variables independently. But some people say we can imagine independent variation and say, okay, that's your surgery, right? You're basically saying, I'm going to shut down equation 2. Many of the economists in them would say, wait, if I shut down the supply equation, by God, that might affect the demand equation a lot. People will go rushing out, buying. So there's an issue about that. But that argument is not fully satisfactory because clearly, and this is where the whole notion of causality really requires primitive structures, we can also imagine a model in which we have, as a part of the model, that x1 is identically equal to x2. So I really can't imagine any variation. So the question then becomes, my imagination by itself is not that much. I can imagine it both ways. How do I actually think about doing this? Well, I think we know how to proceed in this framework. The standard way is to imagine that there are x effects on y1 and there are x effects on y2, exclusions. And this is the standard approach. And now what did the exclusions do? They don't shut anything down. They independently vary y2 relative to y1 in that equation. So I go back up here, and I have some exclusion restrictions. I go back to my equation system. Then basically I can say, yeah, well, I have x2 excluded from the model, but it's there in the reduced form. And I can use the variation in x2, holding constant x1, holding u1 constant, or even setting u1 to 0, and come up with a causal effect of y2 on y1. So in that sense, I can actually identify the model through a thought experiment. There are many ways to do that. Instrumental variables, this is just indirect least squares that I'm talking about right now. And this holds true in a general nonlinear model as well. So for example, if I write this model, here we go. If we just write down the general, we can define exclusion this way, in the non-parametric simultaneous equations, and then we can recover, again, the parameters of these equations by taking ratios of derivatives from reduced form parameters. So phi's are the reduced forms, and from that we can cover the structural equation. So we can get the causal effect. And without surgery. Surgery is one way, possibly. You could imagine it, and you can think of many different ways to essentially create this. And so here, just using in terms of the mediation analysis, this is again Klein and Goldberger, goes back to the 50s, but basically going back to Sewell Wright, Klein and Goldberger, Tile in 58, we can see that we can get the reduced form estimate of x1 on y1, and we can then say, what's the total effect? Well, the total effect of x1 on y1 comes again from this system here. That's our reduced form. But I just showed you how to come up with the structural parameter. This I can get from the reduced form, and I get this from the structural parameter given exclusion. There are lots of other ways to do this, so I don't want to say this is the only example. But I'm saying, so surgery is one useful example, but it's not the only. So let me see, how much time do I have left? Minus 20 minutes? When did I give Judea another 5 or 10 minutes? And so I can. Anytime. No, it's fine. Okay, so let me just talk about, so I'm only on topic 4. So I want to talk about trying to at least show where this Haavelmo variable v shows up in the equation system, okay? So this is a general DAG framework. And here but I'm going to use exactly what Judea was talking about. So the notation is atrocious, but it's pretty simple. Y, T for treatment, U is unobservable. V is that Haavelmo V, the thing that's causing all the selection issues. And then we have a Z, think of it as an instrument, and we have an observed variable X that causes T and Y. And then I'm going to play the same trick, that hypothetical variable. Instead of my X tilde, it's going to be a T tilde. And I'm going to essentially go through this. So these are the structural equations. And these are really important, these structural equations. Because this is not here. That's important to ignore. But this is omega, this is epsilon, and this is really showing how all the different sources of the variation comes. X, U, T, causing Y, and equations for T. This being extremely important. So let me just, okay, 20 minutes. That's giving me more well. So let me just use my, this is bad, so I'm going to just do this. If you remember the notation, even vaguely, there's the hypothetical model and the empirical model. And the only difference between the two is in the hypothetical model, I have this do operation. I have this hypothetical T tilde, which means I can then condition on this T tilde, and that T tilde is defined to be independent of everything in sight. And it's in my mind that I did it. God didn't tell me, maybe God told me, but I don't have any real reason to believe that, but it's a hypothetical intervention. Galileo did, I guess, according to the previous time. So basically, and this is the empirical model, where we're trying to actually go back and test whether from the empirical model we can actually see what the causal effect would be. So that's the plan. And what I just want to talk about different mechanisms for doing so. Here I would also, and here's a challenge, make a slight adaptation. So this may be happening too quickly in real time here, so maybe I'm not being at all clear. But remember, the U's are the things associated with Y. The T tildes are associated with Y. That's the hypothetical. But in the data, the U is generating the Y. The T, this is the treatment effect on Y. Here's our candidate instrument. And these are the unobservables V. And this thing is what's haunting us, this V. This V is correlated here. It's correlated here, so there could be a spurious relationship. That's the nature of the problem. Okay. Now, the question, though, is, suppose that we can also have T tilde causing U. That sounds strange, but it isn't. The generalized Roy model I put up earlier is exactly that case. And so I can draw this case here, but now what we have is that T tilde is causing that unobservable. You already put up the slide where I had Y1 and Y0, the mixture, the quant switching regression equation. And it's exactly what this case covers. It's allowing then to say that the unobservable, the actual observed y, could either be y1 or y0, and my choice of the hypothetical treatment affects u. And I would pose as a challenge, maybe for the discussion, exactly how the do calculus would analyze this particular model in the generalized Roy model. To my understanding, it won't work. But it doesn't matter. There are lots of methods for identification.
It's a research question.
The research question is one of the many I said before. I'm, for example, interested. Let me say specifically what my research question is. I am interested in knowing what is the marginal gain to somebody to go to college, the person who's just indifferent between college and high school. That's the question. And I'll show you how to answer it. And I don't think do will do it. But let's see. So now I'm being deliberate. we have time to argue. So what I'm really saying, see, I did this deliberately, but why not? You only live once, so enjoy it. So here, this is the switching regression. I realize that people claim this. I first saw it in quant's classes, but that's another story. And this is the continuum of treatments. So this is just the standard story. And this is the Haavelmo version of the model. And I'm not going to go through treatment effects. I already announced my question. So then, what are the identification strategies? So let me just lay out very briefly the identification strategies, because I don't really have time to go through in great detail. But I will draw a few pictures and talk about different strategies. So these are the classes of models we're interested in. And I would actually take the generalized Roy model as the one that I personally worked on a lot. But here's one source of identifying assumptions. These look familiar. These look like instrumental variable assumptions. And they are, really, except for some small details. But we think of Z as an instrument. We think of counterfactual outcomes. The finiteness can be relaxed. We can work with quantiles. Population contains a treatment and control group. And this is just a technical detail. Things get more tedious. So those are kind of standard assumptions. But what I want to maintain, and this comes back to the touchstone of Haavelmo, that all valid strategies are controlling for V in some form or another. And I just want to sketch how they control for this V. So we have this V, right? That's the important notation. V is this contaminating variable introduced by Marshak and Andrews in 1944 on the heels of Haavelmo. V is what's causing the problem. U is causing the problem in Haavelmo. V is a slight addition. But let me just, V is where the modern literature is. But how do different strategies approach this? And here, if time permits, I'd love to go through every line in this table. Oops, wait, yes. That there are at least, I would say, 6 methods that are out in the literature, all of which are solving this latent variable V, all of which are trying to control for this V. First of all, is the notion of matching. Everybody does matching. Jeff loves matching. But basically, the idea is we have V. If we can measure V, then we're done, right? We can condition on it and we're home free. And there's some perturbations of that method where we measure V, but we measure V with error. But we might have some proxies for the error, so we can still do matching, but we need to be a little more subtle. Late is actually also dealing with V. And that's more subtle. And this is exactly where I think we're on the same page. Because if you take the structural interpretation, you take the analysis of Bitlesso. Bitlesso proved a theorem some 10 years ago now in Econometric, very important paper. If you take the late-like assumptions from Imbens and Angrist 1994, and you map them into a standard generalized Roy model, there's if and only if. But literally what you find is that a random variable V emerges as a prediction of the model of late. There is a latent variable sitting inside the IV, and I'll show you exactly what late does. Late is essentially showing you how you can condition on the parameter, but not for a particular value of V, like matching, but for a range of values of V, and that's the difference. And then there's a refinement of this, which I did with Ed, which is saying we can actually find the value of V. Without measuring it directly, we can actually tell you at what V you're conditioning on. Principal stratification, or stratification, which I think usually you said there were people who were familiar with this and been going through it, is another example of this, where essentially the strata in that model is encompassing the set of V. It's a if and only if. You can literally, given the structural equation interpretation, the strata provides some coarser assessment, just like late. And in fact, under certain conditions, the principal strata model is equivalent to late. It is late, so it's the same as late. And then finally, something that looks like it's from outer space, but it's right here, is basically the heterogeneity model, so-called random effects model, where we integrate out V, and there are various extensions of it, right, Jeremy, where we can integrate on V conditional on X, and so we can extend even what I put up here. I just decided not to gild the lily. So these are the main things. So matching, we know. I don't think you need me to tell you about matching. Matching on mismeasured variables. We have some old papers on this now. Live and late. Let me talk about that, because that's a little more subtle. A little more subtle. I don't know if it's well known, but what happens is, in this paper with Bitlesso, going back to actually 1999, we show how if we can get our hands on V, but we get our hands on V in a very different way. We don't directly measure V. What we're doing is actually showing that we can compute certain derivatives of the outcome function with respect to the propensity score, and we can show that you can identify essentially E of Y given T given V at every point of support of the propensity score. So in that sense, you basically are controlling for V. Even though it doesn't look like you're controlling for V, you actually are. The control function approach, which goes back, I think, to Lester Telser, and more recently Blundell and Powell and many others, is basically directly solving for V. It's using one equation to invert out and find a V. Okay, these are all just methods that are called control functions. I don't know if we have time for stratification. Do you? How much time now? 10. Okay, well, let me just sketch stratification, just to make a claim rather than, because I'm not going to have time to fully develop this. But unless everybody knows stratification. Everybody knows the stratification procedures? They do? Completely? They know that it's isomorphic to essentially a spanning of the space of the V, latent V random variable that appears? No. Okay, good. I bet you don't. We didn't know it either until about 6 months ago. So we're I was kind of hoping. Okay, but what are strata? Strata are basically, okay, so Z is our instruments, right? Those are our strata. And it's a clever idea. So I'm not going to, again, I'm not trying to trash anybody. I'm just trying to put it in a framework. The strata is basically, and this is going to define it as, in a very abstract way, as an ordered random vector of treatment assignments for T given Z. But instead of just doing it hypothetically, let me show you a strata matrix. This is a strata matrix. And this is the thought experiment. This is all in my mind right now. A is what I'm going to call the strata matrix, or strata matrix, S. These are the different strata. And so it's not going to be a deep thought. This is binary outcomes. Yes or no. Treated, yes or no. And basically, I have 3 values of the instrument, Z1, Z2, and Z3. And a 1 means the event occurs. The guy smokes, or he dies of cancer, or whatever the event is. And in stratum 1, it says for all values of Z, people are going to be doing this thing. And stratum 2 is saying, for Z1, the person isn't going to do it, but at Z2 and Z3, he is going to do it. And here's another case where at Z1 he does it, at Z3 he doesn't. He does it, but at Z2 he doesn't, and so forth. So there are 2 to the 3 possibilities, and that's why there are 8 elements in this matrix. So that's the A matrix. Okay. So the question then is, what are strata? That's strata. But now what are the stratification procedures? Now this, I think, is interesting. So the idea is really the following. You partition the sample of strata so the treatment is independent of the outcome given the stratum, okay, for each subset of the stratum. And you could identify, therefore, counterfactuals if I can do that. But that's like wishing that these counterfactuals would come to me in a dream right now. I haven't told you how to do it. And so the problem with stratification is that the proposed partitions that guarantee independence aren't known. So if I knew what they were, I'd be home free. So we use the concept of stratification and structural equations to link us right back to a mixture problem. And this takes us to the final point. So let me just, these are hypotheticals. These are the kind of models. I'm stripping out a lot of the variables. All I'm going to do is say, here we have the Z goes to T, goes to Y. V is our problem. This is the original problem. This is the empirical model. This is the hypothetical model, so that's nothing new. This is a model where we have the strata. And so what happens in the hypothetical model is, again, my t tilde, your do operator, is basically 5 minutes. Now I'm running out of time. T tilde goes to y. V is causing y, but this thing is an independent manipulation not affected by v. V goes into the strata, and the strata affects t. I haven't told you quite how to form the strata yet, but I will, and I hopefully will. So I don't know if that notation is clear, but I think it's reasonably clear. So we can then essentially allow us, you can show that the principal stratification are essentially allowing us to control for V. I skipped over a slide. In fact, the slide skipped over me. Oh, here it is. Yes. So basically, we have this finite participation. But the important thing is right here, and this is going back exactly to Judea's talk, that associated with each one of these t's, whether it's 1 or 0, that's our, the value of s, is going to be a z, a v, and x. X is just sitting in the background here. And that means we're going to get unique map of these v's into the t. It's a function, okay? Not a correspondence. And what that means then is that v is going into t, and what that means then is essentially we're able to come up with this claim here, that the support of v is the union of disjoint sets. That comes from the functional nature. Again, the structural equation is being used in a fundamental way as stratum. So in other words, we're partitioning the sample space. It's just a coarser partitioning. It's like a balancing score in matching. Okay, so let me, here, running out of time, but they're coarse partition of V. And so literally, we can do it 2 ways. I can condition on V and get independence, or I can condition on the strata and get independence. And the strata are maybe a coarser participation through the structural function of the underlying V. And so what we can basically say is, okay, the counterfactual, the yt that we're trying to get our hands on, depends on y of t given this unknown stratum. And here's the probability of the stratum. This is not by itself a promising equation, since I don't know this and I don't know this. But hope is on the way. The identification problem is, what do I know? Well, I know E of y given t and z, right? I can condition on that. Those things I know. I also know the probability of the stratum, t given z. So I know that. So those things I know. And what does that help me do? Well, it helps me in the following way. And here I really got to, okay, so these are the identification results, but I got to skip out. So P is going to be the propensity score, Q is the data, and this P sub s and Q sub s are basically the hypotheticals. These are the probabilities of the strata, and these are the outcomes given the strata. So I'm trying to get my hands on P, S, and QS. So what can we say? Well, I just gave you the A matrix. I just showed you an example of it. So let me just go to work. And since I only have 3 minutes, I will just assert this, and hopefully it'll come up in the questions. We have an equation. The equation is that the probability of T given Z, which I observe, depends on the stratum matrix, which I can clearly construct, right? And on P of S, which is unknown. So now I can basically say, well, look, I don't know exactly P of S, but I can compute the generalized inverse in this discrete case. So I do know this structure, at least such as I get from a generalized inverse. But now what we can say is the following. Here we go. So we can get the observed variable there. These are constructed from the strata. And this is stuff, the bottom part is observed. We're trying to get our hands on the unobserved stuff on the top, the stuff in the triangle. So how do we proceed with that? Since I have like 3 minutes. Or is it 30 minutes, you said? I'm sorry. Okay, let me just see. Oh, boy, this is such a nice point. Let me skip over all this. What this is, essentially, if you look at it closely, it's a mixture problem. We're really getting a mixture problem. And we're asking, when can we solve a mixture problem? And here I'm just going to assert a theorem that's old. It goes back to the literature in the 1960s. I've forgotten the author, but it's a classic book by Rao and a bunch of others. That we just have if we want to solve this mixture, we have some data on the left and we actually want to try to find out what the mixing probabilities are in the kernels. A necessary condition for identifying all finite mixing distributions associated with the family of probability measures that are indexed on theta is that the probabilities be linearly independent. And so we want that A matrix, which is playing my role in that equation. If you have any good visual memory, you might remember the A was like the middle of that P, script P sub theta, a calligraphic P sub theta. So if you can remember that, and here I'm just going to have to assert it. But basically what we're looking for is some linear independence conditions. Now how do we get the linear independence conditions on A? And let me conclude with this and show you one very nice. So I want to be able to solve these kinds of equations. So how can I do it? So this is a binary case. Here we're going to assume we have 3 instruments, the same case I showed you before. This is all possible matrices A. Now I can come up with a bunch of numbers. I'm getting bounds from the generalized inverse. But now suppose that I go back to the late literature and say, I want to impose monotonicity. So suppose that I have elements that are satisfying monotonicity. I think you all covered monotonicity, and it's not really anything monotonic in a functional way. It's really just saying that we get uniform movement. But here what I'm saying is, just say for particular values of z, this is probability of treatment given 1, given zj, treatment in 1 given zj prime whenever j is greater than j prime. It's like uniformity. People are more likely to go in versus not. Suppose that I do that. Then you can show the following, and I'll just show you what comes directly from that. The A matrix, if you recall, was this 8-row matrix. Now suddenly a bunch of rows have vanished because I'm monotonic in Z, which means then I reduce the rank. And it turns out I have enough information now to invert that matrix and solve uniquely for the stratum probabilities. And so literally what I'm getting out is basically saying these functions here. And so I guess if I have to stop, let me stop. I'll stop the way you stopped. I'll stop gradually. So this is the Bitlesso theorem. I was saying there exists a function tau of v such that treatment assignments t are defined by this. So literally, people say, oh, I don't like these equations, and I don't like the separable discrete choice model. That means you don't like late either. This is if and only if under some mild regularity conditions. Late is assuming the existence of a function tau of v with probability 1 exists there. So late implicitly assumes a v with these properties. And so the monotonicity property is basically assuming this additively separable model. You don't have to do causal analysis with monotonicity. There's some very nice work by Gautier and Hoderlein and some other people as well who've relaxed that assumption, Lars Neschheim and others. But what is late doing? In this case here, late is basically identifying E of y1 minus y0 conditional on v within a certain interval. How do I get the v's? By basically off of the upper support and lower support of the propensity score. It's that simple. And so that's why literally all of these methods are conditioning on v. So let me I'm getting carried away here, literally. Let me look at the stratification treatment effects. No, I'm not going to do that. Let me just assert the following. From this argument, under monotonicity, remember the left-hand side were these objects here that I couldn't get my hands on? Those are the unobserved variables. Those are unobserved, but I can link those directly under monotonicity to these observed objects. Okay, then given that, literally, the stratum treatment effects are literally the lates under monotonicity. There are other ways to get stratum treatment effects. Any way to get the rank on that matrix A, that's true of almost any identification result. You want some matrix to have full rank, but in this case here, it just is like if and only if. So I'm gonna stop. I mean, there are lots of other things to say. Let me just. I'm not going to talk about this. I don't have time, and I doubt there'll be such curiosity. But I would just summarize everything with this equation, which I think is fundamental. We observe this data. This is y given t and x. Remember, in the generalized Roy model, y could be a mixture of these two distributions. It could be like the switching model. This is the counterfactual. We're conditioning on v. This is the distribution of v given x. And here we could use some of these results that Jeremy, others have been doing. The question is really we want to solve from this equation here on the left under regularity conditions to solve here. I gave you some ways to do so. Literally, under rank conditions on this matrix here, under monotonicity being one way to achieve those, I can really end up. But all of these methods are essentially controlling for V in various ways. Under matching, this becomes degenerate, right? I put point mass at the value on which you match. Under the control function approach, it's also degenerate, which is very similar to matching. Under the random effect model, which I haven't really talked about, we integrate out the V conditional on X, and we also control for it. So there are different identification conditions, and I would be curious to the extent to which the do operators would work in identifying these general models, the do calculus, not the do operator. So this is the same table I had before, and I should probably stop at that, other than, so I'm over already. I would just say we did have some discussion, and unfortunately we'd run out of time, I hope we have time to talk about it, about mediation analysis, where we actually can use the structural mediation analysis. We have a new paper. By the way, I should have introduced my co-author. He's responsible for all the good ideas in this paper. That's Rodrigo Pinto. Stand up, please. Rodrigo, yes. Sorry, I got carried away. But I think, so I guess to summarize, I would say this. I don't disagree with much of what you're saying. I really don't. Except to say that I think economists aren't quite as ignorant as you say. I think maybe that some economists are, but some of everybody is ignorant, and there are a lot of wise people in every field. I do think that this structural approach, I do think these ideas are coming together. And I completely agree that if we just stop with this kind of potential outcomes model, we're not modeling the mechanism of treatment assignment, we're not really talking about generating counterfactuals in new worlds, and we're not solving this apparently impossible problem P3, where we're talking about forecasting the Frisch problem. It was consumed by Frisch. I'll just end with a note. Klein was here for many years, right, in the 1950s. Wasn't he basically fired from Michigan for being a communist? Right, okay, fine. So anyway, too bad. But well, and Goldberger was trained here and was very bitter about this experience. But I'll tell you something, and this is just going back to this period. So I'm not trying to just glorify some mythical past. I talked to Klein. Klein has this paper. The obsession, remember, those guys coming out of the Second World War now wanted to use data from the 1930s to make a forecast of what the post-war world would look like. So the mythology is that somehow all these Keynesians were completely crazy, the marginal potential to consume. Well, Klein has this paper published in 1946 and 1947 that essentially does try to forecast what the world would look like in a post-war world without depression, with full employment, and with all the liquidity that was built up by, the assets and the tight economy during the Second World War. It was actually quite accurate for the period over which he was forecasting. And that was kind of viewed as a major triumph. Just like in the Bay Area rapid transit study that McFadden did, that was actually pretty much on target in terms of predicting the counterfactual model of how it was that the structure of you built a new railway system, a new street railway system in San Francisco, or a rapid transit system, and you wanted to forecast what would be the ridership of that system. That's an amazingly challenging task. And he came very close. I mean, I don't know how his forecasts are now. I don't think he was forecasting 30 years in advance. That's question P3. So I do believe that at least an important subset of economists have thought about these questions and have a lot of answers. And so, but I think it's completely sympathetic, completely incompatible with what you're saying. You don't look too happy right now, but that's okay. No, but I'm saying that I do believe that the economists and the sociologists and the group working with these equations who write down these models probably are very sympathetic to what you're saying, but I also believe that some of these ideas are there before. But that doesn't mean there's not a lot of room for improvement. Certainly the non-parametric, versions of these things are challenging and computationally and theoretically. So I'll stop at that. Thank you very much.